So we know that you have something like that. Then you have the structure going upwards. Okay. So it's just a sketch, okay? 8, 2, 4, 6. Right, from this view. Then after that, you put in your forces. Okay, you sketch your forces. So I have a force over here going at 150 pounds. I have a force coming in this direction at 200 pounds. I have a load over here pushing at 50 pounds. And then I have another load over here pushing at 150 pounds. Then after that, immediately sketch your element, right? This is your element H. And over here is your element K. And then at the same time, you sketch your geometric axis relative to the element. Okay, so this is the straight line. Okay. So the first thing that you realize now, right? We can, so the first thing, the next thing that I will highly recommend you to do is to ignore or step number 5, which I'm going to write down here. Ignore the dots and crosses. Okay, don't analyze anything that look like a dot and a cross. Don't analyze them yet. Okay, so we only analyze from this view. We only analyze an arrow like this. Okay, we just do that. So the first thing that we realize that 150 does has a perpendicular distance, right? So we realize that we have indeed we have a perpendicular distance over here, right? And this distance is 10 inch, right? And then if I were to draw my transformation again, this is rotation about Z, right? So you know force multiplied by perpendicular distance, we are going to have a moment, right? You can see over here. So we can have a moment about the what? About the z-axis, right? Why? Because with the 150, the green line, okay, the green, okay, the green line, okay, this is the deformation pattern. Okay, so over here, this is our deformation pattern. And if I were to complete the deformation pattern, right, this line will still be straight. And if we were to draw with respect to time, the 150 will be coming down this way. Okay. So this is 90 degrees. This did not change, right? You can see this axis over here. This is 90 degrees, and this is 90 degrees. Okay. It's still 90 degrees. Why it's 90 degrees? Because at this point, where the dot is, there is no resistance force. So it's allowed to move, okay? Whereas at this point over here, right, there is a what? Resistance. Okay, there's a resistance force. So that's why you see a deformation pattern along the green axis, okay? But the structure, the vertical structure, did not bend at all, because at that junction over there, at the dot that I've drawn, right, is allowed to what? Deform, right? So from here, immediately we know, right, we have a moment about Z, and the moment about Z will be equal to 150 multiplied by 10. So this is equal to 1,500 pound-inch, and is going in a clockwise direction. Okay. So now we already know, right? Over here, you have compression, exactly like what we learned last week. And then over here, you have tensile. The formula that we are going to put in, right? If you look at the formula that we're going to put in now, so mz will cause a stress in the x direction. So this will be equal to mz over izz multiplied by y, right? So if you look at element H, right? If you look at element H, stress X will be equal to what? Tensile, right? It's going to be positive. And if you look at element K, right? Stress X is equal to 0 because it's at the what? Because Y is equal to what? 0. Okay. So not only you know there is a moment about X, okay, you also a moment about Z, you also now can identify whether it has tensile or have compression. Okay, so this is one way of doing it. The rest are all dots and crosses. Don't analyze them. Okay, then from here we look at a different point of view. Okay, we look at a different point of view. So I'm going to take this image with me. Right, we're going to look at a different point of view now. So the next point of view that I would like to do is we'll look into the XZ plane. Okay, so this is my X, and then this is my Z. Then we have rotation. Okay, and over here you have rotation in Y. Okay, so I'm going to sketch again. Right, and then there is a round, right, and then I'm going to draw the forces. So you have over here 150 pounds. You have over here now 200 pounds. And then you have one over here at 50 pounds. And then you have one over here running at 150 pounds. Okay. And then you sketch in your element. So now this is your element, right? Element H. And then over here, you have your element K. Again, sketch your geometric axis. Right, this is your geometric axis. Okay, so this is your geometric axis relative to the elements. Right, so the first thing that we can immediately identify is Px right? We can almost immediately identify Px is equal to 150 pounds, right? So this is your axial load or axial force is in line with the what? Geometric axis, right? As long as it's in line, it's going to be your what? Axial force, okay? So now you view from here 150 pounds will generate your axial force. So theoretically, right? I mean, if you are familiar with bending moment theory, okay, if you have 150 here, right, the 150 will be transmitted about the axial load. But it's difficult to visualize this, isn't it? Right? It's difficult. Why have to shift it? Okay, because of this the offset, which is under eccentric loading, will cause an axial load, right? So if it's difficult to see this way, okay, oh, sorry. If it's difficult to see this way, then just look at a different point of view. Now you can see that the 150 is exactly acting on the what? Geometric axis. So that is your what? Px. Much more easier to see, okay? Then the next one we have is we are going to have, I'm going to say forces that are going up is positive, right? So it's up to you, okay? Or yeah, I'm going to call forces that is going up is positive. So now we are looking at the shear force in the z-axis, along the z-axis or parallel to the z-axis. So going upwards is positive, so you have 150 plus by 50 minus by 200. It happened to be equal to what? 0 pound. Okay. Then the next one that we're going to do, right? All these forces. What do you mean by all these forces? The 150, the 50, and the 100 are applied what? Perpendicular to the what? Geometric axis, right? So we know there is perpendicular distance. So we know that there's a distance from here to here, and this is equal to 4 inch. And there's another perpendicular distance from here to here, and 6 inch. As long as a force and a perpendicular distance, you are going to generate a moment. And we know that the moment will be about the y-axis. So you declare, okay, it's up to you to declare now. Declare what? So you call anything that's causing a clockwise moment or a counterclockwise moment will be positive. So this will be moment about y. Before I go on, okay, my bad. I think before I go on, we know that stress X is equal to Px over A. Yes or no? Right, there we know. And when that's the case, the axial load, right? Let me move this axial load, right? So you know that this will be equal to stress X at point H and also equal to stress X at point K, right? Because it's just force divided by area. The next thing that we look at is our shear force, Vy. Now, in this case, we happen to be lucky. It's 0. If it's not 0, it will contribute to a shear stress, which is equal to Vz over Iyy Qy over T. Okay. So in the next, after this, in the next chapter, I will teach you how to calculate the shear stress. Now we have to look at the moment about y. Okay. So the moment about y going anti-clockwise. So the 150 at the bottom will generate anti-clockwise. So it's positive. So 150 multiplied by 4 plus by 50 multiplied by 10, then minus by 200 multiplied by 10. So this work out to be 150 times 4 plus by 50 times 10 minus 200 times 10 is equal to minus 900 pound each. Okay, it's equal to 900 pound each. Let me calculate. Let me calculate again.